All right, so today I'm going to be going through exam 2 from spring 2023 for AAE 204. Go ahead and start on problem 1. The circular shaft shown in the figure below has a solid section AB and a hollow section BC. The inner diameter of the hollow section is 3 centimeters and the outer diameter is 4 centimeters. And that's like the entire rod. The length of section AB is 20 centimeters, and the length of section BC is 30 centimeters. And the shear modulus of the material is 75 gigapascals. So for part A, calculate the internal torques carried by sections AB and BC. And for part B, calculate the angle of twist at C. Part C, we have calculate the minimum and maximum shear stresses in sections A, B, and BC. And then for part D, we have if the 100 Newton meter torque at C was removed and replaced with a fixed support, describe without performing any calculations how you would solve for the internal torques in the shaft, and write no more than 3 complete sentences. So the problem's asking for a couple different things. So part A asks for us to calculate the internal torques carried in each of the sections. And then part B is going to ask us to use the internal torques that we just found in order to calculate what the angle of twist at part C, at section C is. And then part C is going to ask us to use those same internal torques we found in part A to calculate what the minimum and maximum shear stresses carried in each of the sections are. And then part D is basically just asking for what would happen if the rod was fixed at both ends instead of just the one. So let's go ahead and start by calculating our internal torques. And to do that, we're going to draw our free body diagram. So let's go ahead and do the free body diagram of the rod as a whole first. We'll just label that. So we've got torques at B and C, and then at part A, we're going to have a reaction torque. We'll call that RA. All right, so if we're just looking at this free body diagram, we can see that we know what B and C are, and we can guess intuitively that the reaction torque at part A is probably going to be the sum of B and C, just in the opposite directions. But let's go ahead and do our equilibrium equations just to check. So we have TRA plus TB plus TC equals 0. And remember that course convention, positive torques usually point to the right and negative torques usually point to the left. So we're going to have that TRA is equal to negative TB minus TC. So TRA is equal to negative 150 minus 100. So that's going to be negative 250 Newton meters. So pretty much what we'd expect. Now, to calculate the internal torques carried in each of our two sections, we're going to split the rod in each of the sections. So we'll make a cut here, and we'll make a cut here. We're going to make one cut at section B. So for the left-hand side, we're just going to have TAB, and that's the internal torque, and then TRA. So sum of torques is going to be TRA plus TAB equals 0, and then TAB equals negative TRA, and it's going to be 250 Newton meters, since we found TRA to be negative 250 in the previous step, so it's just going to be the opposite of that. Well, let's go ahead and do the right-hand side. So we have torque C, and then we're going to have the internal torque BC. So if we take the sum of our sections, TC plus TBC, except in this case it's going to be TC minus TBC because we have TBC pointing to the left, so it's going to be negative. That equals 0, so TC equals TBC, which equals 100 Newton meters. All right, and that does it for part A. So we have our internal torques. Torque AB being 250 and torque BC being 100. All right. Oh, I never underlined that. Whoops. Let's go ahead and do part B of this problem now. They're asking us to calculate the angle of twist. Quick reminder that the formula for angle of twist is going to be, in an individual section, it's going to be the torque in that section times the length of that section over the shear modulus in that section times the moment of inertia in that section. And then the overall angle of twist for a whole, if you're doing it over multiple sections, it's just going to be the sum of it in each of these individual sections. So we have to find the angle of twist in AB and the angle of twist in BC in order to find out what the angle of twist at this point C is. So, but first things first, we're going to need to calculate what the moments of inertia in the rods are in each of the sections. So remember that the formula for the moment of inertia in a solid rod is just going to be, and this is a solid circular rod, I should say, is just going to be 1/2 pi r to the 4th. So that's going to be 1/2 pi times, and I like to do everything in meters just so I know all my units are going to work out nicely. Quick reminder that in the problem statement, we were given the diameters of each of the sections, so make sure if you use this particular formula, make sure that you cut that in half. I believe there's another formula that has diameter instead of radius, but to be honest, I cannot remember it off the top of my head, and I don't know, I've just always used the radius because I find it easier to remember. But yeah, so point is, if you use a formula with the radius, make sure that you use the radius and not the diameter. So the radius of our solid circular section is going to be 0.02 meters. And that's going to give us a moment of inertia of 2.5133 times 10 to the -7th meters to the 4th. All right, And then let's go ahead and find it let's do the same thing for section BC, except this time we're going to have to do something else because the formula for a hollow rod is going to be different from a solid rod. It's going to be 1/2 pi times the outer radius to the fourth minus the inner radius to the fourth, which, if you think about intuitively, kind of makes sense, right? Like, you're basically taking, what if we have the moment of inertia of this rod, if it was completely solid, and you're subtracting out the moment of inertia that would be present at the inner diameter that you're taking away, is how I always remember that particular formula. Although I should say, you shouldn't have to actually memorize any of these formulas. Like, these are very good things to include on your crib sheets. So 1/2 0.02 to the fourth minus 0.015 to the fourth. And that's going to give us the moment of inertia of the hollow section as 1.7181 times 10 to the negative 7th meters to the fourth. All right, and now we're ready to find what the angle of twist is. So the angle of twist at C is going to be the angle of twist in section AB plus the angle of twist in section BC. So TAB times LAB over G times IAB, and the whole rod has the same shear modulus, so that makes this a little bit simpler in that respect. And again, I'm just putting everything in kind of their singular sort of units, so I don't have to worry about things canceling out weird. And adding those together, we're going to get a total angle of twist as being 4.981 times 10 to the negative 3 radians, because this formula gives us the angle of twist in radians. And there's our answer for part C. All right. On to our part C. Reminder that part C is asking us to calculate the minimum and maximum shear stresses in each of our two sections. So let's go ahead and start with section AB. So we have the formula for tau max is going to be calculated by multiplying the internal shear stress times the radius, or sorry, not the internal shear stress, the internal torque carried in this section, sorry about that, over the moment of inertia. So that's going to be 250 Newton meters times 0.02 meters over 0.5133. And that's going to give us a maximum shear stress of 14.894 megapascals, or 14.894 times 10 to the 6th pascals. And then we have the formula for tau min, the minimum shear stress, as being R point over R surface, and that should be R point being the most internal point of the rod, so times tau max, and that's why we found tau max first, because we needed it in order to find tau min. So in this case, we're doing the solid section AB, so R point is just going to be equal to 0, so tau min is just going to be equal to 0 as well. All right, and now for section BC. So same thing for tau max, except we're just gonna be tau BC times R over IAB, and I should say that again, R is the outer radius, it's the maximum radius in your rod, so and again, these are good formulas to include on your crib sheet. Also, example problems. If you have room for example problems, highly recommend adding those as well. I personally find them to be extremely helpful because sometimes you see the formula, but you don't necessarily know what to do with it. And I find that that can be helpful. So, but yeah, so we have tau max for section BC is going to be 11.641 megapascals, and then we can calculate tau min. Again, R point over R surface times tau max. So that's going to be right, and that's going to be 8.731 megapascals for the minimum shear stress in section BC. All right, so now we just have part D of this problem. So, reminder, part D is asking us if the 100 Newton meter torque at C was removed and replaced with a fixed support, describe, without performing any calculations, how you would solve for the internal torques in the shaft, and write no more than 3 complete sentences. So the trick to recognize here is that if we just rely on our torque equilibrium equations, we're not going to have a solvable system of equations. We're going to have too many unknowns. So we have to add another constraint in, and that constraint is going to be a geometric constraint. So if we fix the rod at point C, replace this with a fixed constraint, there is going to be no angle of twist at section C, so we will have that additional constraint in there as well, and we can therefore solve for our and then we can therefore solve for our internal torques in the shaft. So you'll have to create your equilibrium equations. And then create your geometric constraint, namely, again, that there is no angle of twist at point C in this rod if you fix the end, and then you can solve for the internal torques from there. And just what that would look like creating that geometric constraint, you would essentially just have that TAB times, I'm just going to call it C for all of the constant stuff, being the length and the moment of inertia and the geometric constraint. And not the geometric constraint, the shear modulus, plus TBC times C2 equals 0. So that would be your geometric constraint. But again, since this problem doesn't ask for that, you don't have to actually solve that equation out. Like, they just want you to explain how you would do that. And keep it short and sweet. The graders don't want to read it as much as you don't want to write it. But yeah, so that's it for problem 1. Let's go ahead and move on to problem 2. So, oh, that's right. The PDF they gave me did the weird thing. So, problem 2, they're giving us the figure shown here, and then part A, calculate the reactions at supports A and B. Part B is asking us to find the internal shear force and bending moments in the beam. And then part C is asking us to sketch the V of X and M of X diagrams. That would be the shear and moment diagrams. And they want us to label the minimum and maximum values and indicate their locations on the sketches. So, pretty straightforward question. Solve for the reactions, use those reactions to help find the internal shear and bending moments, then use the equations you found in part B in order to create your diagrams. So let's go ahead and start with part A, calculating our reactions. So let's go ahead and start by drawing our free body diagram. So notice that we have a pin support at point A and a roller support at part B. Quick reminder that a pin support is going to have a reaction in both the X and the Y, and that the roller support is just going to have a reaction in the Y. So Rx, Ry, and then Rby, and then somewhere in this overhanging section, for the purposes of calculating the reactions at the support, we're going to replace the distributed load Q of X with a discrete load Q, and we have to solve for the magnitude and location of that. So, in order to find the magnitude of the discrete force Q, you're going to have it'd probably be better if I wrote out what the actual equation was. To replace a distributed load with a discrete, the formula is going to be the integral from x1 to x2 of your q of x function integrated over x. And then in order to find the location of that, it's going to be the integral from 1 to 2 of q of x times x. And then, with respect to x, or I suppose with whatever variable you're using, perhaps they decide to make your horizontal variable something else. But regardless, basically whatever variable you're integrating over that is representative of the length of the beam. So let's go ahead and solve this out. And that's going to be, we're going to have a magnitude of 8 kilonewtons for our discrete force. Oh, that's right, I forgot. You also have to divide by what your Q was. So that formula I gave you for x bar, the location of your distributed force, yeah, so you have to multiply it by x, and then you also have to divide by the magnitude of your distributed Q. So it's going to be 6, 4 times x dx, all of that over and all of that together is going to be 5 meters. So right in the middle of this overhang essentially is where Q is going to be. All right, so now we can solve for our reaction forces. So sum of forces in the x is just RAX, so that's just going to be 0. And then sum of forces in the y, we have RAY plus RBY. Here, make that a little easier to read. Plus Q equals 0. So that's going to give us RAY plus RBY equals 8 kilonewtons, because remember that your Q force is negative because it's, pointing down. I suppose I should have done this earlier, but we'll define up as positive and right as positive. And then we'll take our sum of moments about, I'm going to do the sum of moments about point A. So that's going to give us RBY times its x location minus Q times its x location equals 0. So that's just going to be let's see, B is at 4 meters. That's how that length is. So it's going to be 4 RBY minus 8 times 5. And that gives us RBY as just being 10 kilonewtons. And we can plug that back in to our equation to find RAY. So RAY is just going to be negative 2. So we have all of our reaction forces. RAX is 0, RAY is negative 2, and RBY is positive 10. All right, let's go ahead and move on to part B, where they're asking us to find the internal shear force and bending moment diagrams in each section of the beam. So let's go ahead and start by drawing a free body diagram for the left-hand side of the beam. And remember that we're going to make our cut right at this point B, because that's kind of where the forces change, if that makes sense. That's where our distributed load Q of X starts. So this is a good place to sort of make our cut. So in our free body diagram for the left-hand side, we just have RAX, RAY, and then our internal shear and our moment. There's not going to be an internal normal force, as we don't have any forces in the X direction for this beam, so it's just going to be 0. So our forces in the Y are just going to be RAY minus V equals 0. So we can calculate V being equal to RAY, and it's going to be -2 kilonewtons. And then to find the internal bending moment, there are a couple different ways you can do this. The way I prefer to do it is to just integrate the shear. So we have that dm over dx is equal to v. So dm equals v dx, and integrate both sides with respect to x. And you end up with -2x kilonewtons as being our equation for the internal bending moment for the left-hand side. So let's go ahead and do the right-hand side now. This one's going to be a little bit trickier thanks to that distributed load. Move this over so it's a little bit easier to see. So we have the shear force in the moment, and I'm making the cut. I'm basically taking this as if we're going from the right-hand side, going this way. If you wanted to, you could also take it going this way, but I find it easier to just go from the opposite end of the beam because it means I don't have to worry about all this other stuff that happened before, if that makes sense. But yeah, it wouldn't be incorrect if you wanted to just keep going from the left-hand side, essentially, when you're building your equations. But yeah, so because I'm taking it from I'm making the cuts, taking my portions starting from the right-hand side of the beam, my internal shear and moment arrows are actually pointing in the opposite direction. Because if we started from the left, like our course convention has shear force going down, but since we're starting from the opposite end, we're going up. So we have our sum of forces in the y as being -4, and then remember, it's as a function of x, but we're starting from the right-hand side, so you can't just straight up multiply it by x. It has to be 6 minus x, since we're starting over here at L equals 6 to build our equation, plus V equals 0. So then we end up with our shear force as being 4 times 6 minus x. And then, again, in order to find our moment, we're just going to integrate that. So we have dm over dx equals v, and then dm equals v dx. And then for m equals v dx, so 4 times 6 minus x dx. Now, let's take a minute here. We can't separate this out. Like, normally my first instinct when doing an integration like this is I would distribute this 4 out, or, just pull it out of the equation entirely. But this whole thing has to be treated as a unit in our equation if we're doing it this way. Like, you can't separate this 6 minus x. This is like one thing. So we're actually going to use u substitution in order to do this integration. So our u is going to be 6 minus x, and then du over dx equals -1, and then du equals -1 dx. But yeah, the reason that this has to be treated as a unit is because when you're building your moment equations, you can't separate out that 6 minus x portion. Like, that's really important. If we were starting from the other side, you would maybe be able to get away with it, but because we're starting from the right-hand side, it's really important that we have that 6 minus x bit in there. So we have to use the u sub, so that way when we put it back into our equation, it's going to be treated as a whole unit. And I'll show you that the integration will work out the way we need it to. So this is going to be 4u times -1 du with our u sub, m equals -2u squared, and so moment is going to be -2 times 6 minus x squared. And this is our moment equation. But yeah, if I were to just do this integration straight up like this, if I were to separate it out, so 4 into 6 minus x dx, then I'd end up with 4 times 6x minus x over 2 squared, which would not give me the correct equation. And I don't know, maybe I'm not doing a very good job of explaining why this has to stay together, but it does. Maybe think of it this way, is that because you're starting from the L equals 6 end of the beam, like any unit of length you take is going to have to be subtracted from that 6. Like, if you think about how you generally solve for a moment, it's the force times the distance from whatever point you're taking your moment about. But since we're solving for our internal bending moment, you can't separate that out from that 6 bit because we're still taking our moment about point A. So it would not be correct to just separate that 6 minus x. All right, but regardless, we now have our 4 equations, so let's go ahead and build our diagrams. I'll do my v of x diagram first, and I'll try to make this as even as I can. That's, I say as I immediately make it uneven. All right, that's, close. All right, so let's go ahead and start by just solving out what it's going to be at our important points. So for here's x equals 4. So this is when our switch is going to happen. Remember that from, and I really should have specified this earlier on in the problem, but the left-hand side is from 0 to 4, and then the right-hand side is from 4 to 6. So each of these equations for the left-hand side are valid for this portion of the beam. So from x equals 4 to, so from x equals 0 to x equals 4, our shear force is just -2. So we can just have this here. And then at x equals 4, it switches, so 4 to 6 minus x. Which is just 6 minus 4, so that's going to switch to +8. And then at x equals 6, it's going to be 0. So it's going to, and since it's a linear equation, it's just going to decline steadily like so. So there's our basic equation, and we can label our max and min. So and it is the maximum numerical value, so like the absolute value in this case. So we have our max, it's 8, and it occurs at x equals 4, and our min is 0, and it occurs at x equals 6. Okay, and now we can make our m of x diagram. This one's gonna be a little trickier to build, but still doable. I mean, again, it's not like these have to be the most perfect representations ever. Like, you kind of just need to get the important parts and like what the general shape would be. But like, they're not asking for perfection. Oh, and don't forget to label your axes. This is always an important step, and it's one I forgot to do here. So apologies about that. Don't be like me. Label your axes. Anyways, with the units, so remember from 0 to 4, our moment was negative 2x. So at x equals 4, it's going to be equal to negative 8. And then for our other equation, we also get that it's negative 8. And then at x equals 6, we have negative 2. And that's just going to be 0. So it starts at 0 and it ends at 0. And at 4, it's going to be negative 8. So we can see that, oh, and I suppose I should say at x equals 0, it equals 0. But yeah, so we see that from 0 to x equals 4, it's a linear downward sloping line. And then from 4 to 6, we have a quadratic equation. So it's going to be squared. So it's going to be a curve. And it's going to curve inwards like this as it is a negative quadratic equation, and yeah. And then make sure we label our min and max. So we have our max equals negative 8 kilonewton meters. And that occurs at x equals 4. And we have our min occurs at 0 kilonewton meters. And that's at x equals 6. All right. And we have solved problem number 2. All right, on to problem number 3. A beam is subjected to a bending moment of M equals 5,000 pound-feet and a shear force of V equals 1,000 pound-feet. The cross-section of the beam is shown in the figure below. Cross-section is symmetric about the vertical y-axis. So for part A, we have calculate IZ about the centroidal z-axis shown in the figure. For part B, calculate the maximum tensile bending stress in the beam. And then for part C, calculate the shear stress at a height of 5 inches from the bottom of the beam. So, pretty straightforward problem. We solve for the moment of inertia, then use that moment of inertia to calculate the maximum tensile bending stress, and also use that in part C to calculate the shear stress from a height of 5 inches from the bottom of the beam. So, let's go ahead and start by finding our moment of inertia. So the formula for a moment of inertia, for the moment of inertia of a rectangle is I equals 1/12 BH cubed. And we can see that this shape is made up of 2 rectangles. So we can find the moment of inertia of each of these 2 rectangles and add them together to get the total moment of inertia. So we're going to call this section 1. We're going to call this section 2. We also have to use something called the parallel axis theorem, because this 1/12 BH cubed formula I gave you only works for shapes with respect to their centroids. So you have to use the parallel axis theorem to essentially shift it in order to determine the moment of inertia with respect to whatever point. So the parallel axis theorem is I plus AD squared for any shape, A being the area of the shape, and D, being the distance of the shape's centroid from whatever axis you are finding your moment of inertia with respect to. So let's go ahead and solve this out. So for section 1, we have 1/12 times 8 times 3 cubed plus 24 times 4.45 minus 1.5 squared. Because remember, the D is equal to this distance here, which is going to be 4.45 minus 1.5, because it's halfway, like it's in the center of the shape. So you end up with 226.86 inches to the fourth for section 1. For section 2, do the same process. And remember that in your BH cubed formula, the B is going to be with respect to the axis that is parallel to your centroidal axis, and then your height is going to be perpendicular to your axis you're taking your moment of inertia with respect to. You end up with 418.717 inches to the fourth for IZ2, and then we can add those two together in order to get 645.577 inches to the fourth for our total moment of inertia for our beam cross section. All right, and on to part 2. So, remember that the maximum tensile bending stress is going to occur at the bottom of the beam. So our formula for maximum stress is M times Y over I, and that Y is, again, the distance to the axis, the distance from your axis to where your, the centroidal axis, that is, to where your maximum tensile bending stress occurs. So, but first we have to convert our our bending moment, because they gave us our bending moment in pound feet, but we need it in pound inches, because our moments of inertia were in inches, all of our other stuff is in inches, and this way we get PSI for our units at the end. So we do that, we end up with 60,000 pound inches. All right, so now we can calculate our sigma max. And remember, since this centroidal z-axis is like saying it's like saying y equals 0. This is like saying y equals negative 8.55. So we have all of that over our moment of inertia, and you end up with 794.638 psi as our maximum tensile bending stress. All right, and now for part C. Part C is asking for us to find the shear stress at a height of 5 inches from the bottom of the beam. So our formula for shear stress is going to be V times Q over IZ times T. V is, of course, our shear stress, and then Q is going to be our first moment of area. So, quick little diagram of our beam here. Remember that the first moment of area is calculated by finding Y times A. So area is, of course, just going to be this shaded area here. That's at y equals 5. And the y is going to be the distance from the centroidal axis to the center of this shape, which is going to be 2.5 from the bottom. And remember that this thickness here is 2. So we can go ahead and calculate out our area as 10 and our y as being 6.05, and our first moment of area then becomes 60.5 inches cubed. All right, and now we can plug that back into our shear stress formula. So T equals 1,000 pounds times 60.5 inches cubed over 645.577 inches fourth times 2 inches, because remember our thickness of our cross section in this case is 2. And we end up with 46.857 psi as our shear stress at x equals 5. Or not x equals 5. 5 inches from the bottom of the beam. And thus we conclude problem number 3.